Hello, future engineers. Welcome to my YouTube channel. If you find my videos interesting and important to your studies, please share them to your friends and your friends' friends. That's one way you can keep me going, inspired, and refreshed. And if my videos are important to your studies, also please don't forget to subscribe. Level 31 problem on friction. A half section of pipe weighing 1000 newtons is pulled by a cable as shown. The coefficient of static friction between the pipe and the floor is zero point 0.4. If alpha is 30 degrees, determine that letter A, the tension T required to move the pipe, and letter B, whether the pipe will slide or tip. So here is the given figure. Let's draw the free body diagram. Let's have for our solution the 1000 Newton weight, which passes through the center. Then let's resolve T into two components. The alpha is 30 degrees. Then take note that the distance of the weight from B is R, and from the center to the point of tendency, that's also R, which makes an angle of 30 degrees with the vertical, because the inclination is alpha. Let's resolve the tension into two components, namely T cosine 30 degrees and the other one T sine 30 degrees upward. And friction is, which will be resisted by friction only at B, because the only reaction present is at B when the half section pipe is about to tip about A. So let's investigate or compute T first when the half section pipe is about to tip at B. Then we have T sine 30 degrees. Then NB. Then let's have our equation, summation forces vertical equals 0. So T summation forces horizontal equals, or summation of moment about B equals 0. Take note that when the half section pipe is about to tip, there's no reaction, normal reaction at A. So there's no also friction at A. So the moment of the horizontal component of tension is T cosine 30 degrees times the moment arm. This moment arm here is R cosine of 30 degrees. Then the moment of the vertical component is also clockwise, so plus T sine 30 degrees. The moment arm is this distance plus this distance. So this distance is R sine of 30, then plus R. That's the moment arm of T sine 30 degrees about B. So T sine 30 degrees times quantity R sine 30 degrees plus R, then equals the moment of the weight, which is 1000 times R. Cancelling out R and solving for T, T is equal to 666.7 newtons. Likewise, when the half section pipe is about to slip or slide, then there will be normal reaction at A as shown, and friction is also maximum because the condition is the tension T required to move the pipe, so it is about to move the maximum tension. So friction is 0.4 of Na as shown. So from the figure, summation forces vertical equals 0. So Na plus N sub B equals 1000 plus T sine of 30 degrees equals 1000. So Na plus Nb equals 1000 minus T sine 30 degrees. So it is 1000 minus 0.5 of tension. Then summation forces horizontal equals 0. So we have T cosine 30 degrees equals 0.4 of quantity Na plus Nb. So T cosine 30 degrees equals 0.4 of quantity Na plus Nb. And since Na plus Nb is 1000 minus 0.5 T, substitute here. So T cosine 30 degrees equals 0.4 of quantity 1000 minus 0.5 T. Solving for the tension, 375.2 newtons. So this is less than 666.7 newtons. So meaning When the tension is 375.2 newtons, which is attainable first, then the half section pipe is about to slide or slip. So therefore, the tension T required to move the pipe, and the movement is slipping, about slipping, about to slip, the half section pipe is about to slip or slide, is 375.2 newtons. And to answer letter B, whether the pipe will slide or up or tip, the answer is the pipe will slide. So that's it for this problem. Level 32, if the coefficient of static friction at A is mu sub s equals zero point 0.4 and the collar at B is smooth so that it only exerts a horizontal force on the pipe, determine the minimum distance x so that the bracket can support the cylinder of any mass without slipping. Neglect the mass of the bracket. So take note that the condition is minimum distance x so that the bracket can support the cylinder of any mass without slipping. So therefore, the maximum frictional resistance, which is equal to mu s times normal, is the available maximum frictional resistance at A. So for the solution, so we have here the weight, which is equal to mg. Then we have the normal reaction at B, which is leftward. Then at A, rightward, and frictional resistance upward as shown. So the normal reaction at A is Na, and the frictional resistance, it should be maximum because we're looking for the minimum distance for the bracket to support the cylinder, so it without slipping. So this is mu sub s times Na. So we sum up moment. So therefore, summation forces horizontally, we say that Na equals Nb. Then summation of moment about A equals 0. So mu sub s Na equals mg by summing up forces vertical. So mu sub s Na equals mg. And summation of moment about A equals 0. So we have counterclockwise positive Nb times 200 equals mg times x. So Nb times 200 equals mg times x. Replacing Nb by Na, and Na is mg over mu sub s from this equation. So Nb is mgx over 200 from this equation. And take note that Na equals Nb. So mu sub s times Nb, Na, which is equal to Nb, into this equation. So mu sub s times Na, and Na is equal to Nb, and Nb is given by this. So mu sub s 0.4 times Na, which is Nb, from this equation, mgx over 200, this is Nb, which is equal to Na, and we substituted it from this equation here, then equals mg. Cancel out mg, so we can solve for x. It is 200 divided by 0.4, so x is equal to 500 mm. So that's it for this problem. Level 33, a loaded wheelbarrow is placed on a rough incline. The combined weight of the wheelbarrow and its load acts at the center of gravity G. Part A, determine the maximum angle theta for which the wheelbarrow will not slip. And B, repeat if the wheelbarrow faces uphill uphill. Neglect all friction associated with the front wheel B. So this is the given figure. And in this problem, because we are looking for the angle max, the maximum angle theta for which the wheelbarrow will not slip, therefore the frictional resistance is maximum, and it is equal to mu sub s times the normal, and it only occurs at A. So for the solution, let's have the weight at G, let's call that W. Then the other forces, such as the normal axis and the tangential axis. Then we have the angle here, which is equal to theta, normal reaction at A, then frictional resistance at A, which is 0.8 of NA, which is up to the left because the wheelbarrow is the tangential component causes it to, or tends it to slide downward. Then normal reaction at B. There's no friction at B as stated here. So summation of moment about B equals 0. So we have NA times 29 plus W sine of theta times 20 inches. The tangential component of W is towards the positive tangential axis, and its moment is also clockwise just like NA, so that's why it's plus. So W sine theta times 20. Then the normal component of W, which is downward in this direction, so W cosine theta times 8, so equals W cosine theta times 8. So setting up NA, factor out W, so NA equals W times quantity 8 cosine theta minus 20 sine theta divided by 29. Then we sum up forces along the tangential axis equals 0. So W sine theta, the tangential component of the weight, must be equated to 0.8 of NA. So W sine theta equals 0.8 of NA, and NA is W quantity, 8 cosine theta minus 20 sine theta over 29. Cancel out W, then simplify. 29 sine theta plus 0.8 times 20, that's 16. So 29 plus 16 is 49 sine theta, and the right side will have 0.8 times 8, so 6.4 cosine theta. So 45 sine theta equals 6.4 cosine theta, where 45 is 29 sine theta plus 0.8 times 20, which is 16. So tangent theta equals 6.4 over 45. From here, we can solve theta equal to arctan of 6.4 over 45, or 8.094 degrees. Now for part B, the wheelbarrow faces uphill. So this is the free body diagram, and we have the superimposed the normal and the tangential axis. Then we have normal at A, friction at A, 0.8 of NA this time, and it is up to the right because the wheel tends to slide down. Then normal reaction at B, and of course the weight, which makes an angle of theta with the normal axis. So summation moment about B equals 0. So NA times 29, then equals W sine theta. This is now the direction of the tangential component, which makes counterclockwise moment about B. So that's why clockwise moment about B equals counterclockwise moment about B. So W sine theta times 20 plus W cosine theta times 8. So that means NA is equal to W times quantity 20 sine theta plus 8 cosine theta over 29. Then the second equation is summation forces tangential equals 0. So 0.8 NA equals W sine theta. So it's the same as this, except that the value of the normal component of reaction at A is now W, W times 20 sine theta plus 8 cosine theta over 29. So zero point 0.8 of normal at A, which is W times quantity 20 sine theta plus 8 cosine theta over 29 is equal to W sine theta. So cancel out W and simplify. For sine theta, 29 minus zero point 0.8 times 20, 16 is 13 sine theta. And in the left side, zero point 0.8 times 8 cosine theta, or 6.4 cosine theta, is equal to 13 sine theta. So tangent theta is 6.4 over 13. Theta therefore is arctan of 6.4 over 13, and that is equal to 26.21 degrees. Level 34 problem: a 600 Newton cabinet mounted on casters that can be locked to prevent their rotation. The coefficient of static friction between the floor and its caster is 0.3. Assuming that the casters at both A and B are locked, determine part A, the force P required to move the cabinet to the right, and letter B, the largest allowable value of H if the cabinet is not to tip over. So we have a 600 Newton cabinet which is mounted on casters, and these casters in this problem are locked. So therefore, if they are locked, then friction will be that due to slipping, so mu sub s times normal. So let's have the weight for the solution, then the normal reactions at A and at B shown, then friction, which is 0.3 of quantity Na plus Nb, or in this caster A, 0.3 of Na, this caster B, 0.3 of Nb, so the total frictional resistance would be 0.3 of quantity Na plus Nb. So from the figure, summation forces Y equals 0 and A plus Nb equals 600. Then summation forces X to solve for P. So P equals 0.3 of quantity Na plus Nb, and since Na plus Nb is 600, P is equal to 180 newtons. That's for part A. For part B, the largest allowable value of H if the cabinet is not to tip over. So when the cabinet is about to tip over, the possibility is it will tip over about B. So there will be no reaction at A, there will be no friction at A. So this is now the free body diagram. We have normal reaction, we have the weight of the cabinet, then normal reaction only at B, then the maximum frictional resistance is 0.3 of NB. Since summation forces Y equals 0, NB is 600, then summation forces X, P is equal to 0.3 of NB, so P is still 180 newtons. Then lastly, we sum up moments about B equals 0, clockwise positive, so 180 times H, then equals 600 times 300 mm. So solving for H in mm, H is equal to 1000 mm. Then this is the last problem for this batch. The 180-pound man climbs up the ladder and stops at the position shown after he senses that the ladder is on the verge of slipping. So take note of the statement. The ladder is on the verge of slipping, therefore the maximum frictional resistance, which is mu sub s times n, applies here. So determine the coefficient of static friction between the friction pad at A and the ground if the inclination of the ladder is theta equals 60 degrees and the wall at B is smooth. The center of gravity for the man is at G, and we neglect the weight of the ladder. So for the solution, let's apply the weight which is acting at G. Then we have the normal reaction at B, which is perpendicular to the wall surface, so it is horizontal, and it is frictionless at B as stated in the problem. Then we have the normal reaction at A, and the maximum frictional resistance to the left, which is mu sub S at A times the normal. Then the angle theta is 60 degrees. So the horizontal projection of the length is hypotenuse 10 times cosine 60, so that's 5 feet, since the distance from B horizontally to the center of gravity is 3 feet, and this must supposedly be 5 feet, so therefore this distance is 2 feet. And the vertical distance between A and B is this distance, and it is hypotenuse 10 times sine of 60 degrees, so 10 sine of 60 degrees. Then summation forces vertical equals 0, so normal at A is equal to W. Then summation of moment about B equals 0, so NA times 5 feet minus mu sub S NA times 10 sine 60 degrees equals W times 3, or minus W times 3 equals 0. So since NA equals W, substitute, so W times 5 minus mu sub S W quantity 10 sine 60 degrees minus W times 3 equals 0. Cancel out W, combine like terms, 5 minus 3 is 2, then transpose this to the right, so 2 equals mu sub S times 10 sine of 60 degrees. So from here we can compute mu sub S, which is equal to 2 over 10 sine 60 degrees, and that is equal to 0.2309. So that's it for this problem.